anything. So what we're going to do today is the last two techniques for finding volumes, and they're very different from the disc washer method that we learned last time. So between the techniques, any problem you could be asked to do in a Calc 1 class, you would have a way of doing it. You could say, I can use this technique or that technique, and in some cases, even multiple techniques. So the first technique we're going to use, okay, I'm going to start with a simple concept. If you've ever been camping, okay, and you're taking your camping gear with you, you tend to take gear that's really compact. For example, there might be a set of cups, okay, okay, a lot of you know what I'm talking about. You might have a set of cups where it's cup inside a cup inside a cup inside a cup, and it's really tightly organized. So you have cups of different size and different measurements. This would be a simple camping tool. When my children were little, that they had bath toys that kind of were this thing. So my question is, if I wanted to find the volume of this thing I'm looking at, and I don't mean what does it hold, I mean quite literally the volume of each of these. Imagine that I peel away some of these cups, like I peel away this outer cup. What would I actually see? I would actually see something that looked like this. Okay, I would see something very thin, but it would also be rectangular. Let me give you a simple example. Hold on one second. Grabbing a wad of paper here. Okay, I've got a stack of paper. So I've got a stack of paper right here. And if I ask you, what is the volume of what I'm holding? Not the volume of the whole, but the volume of the solid piece that I am holding. Now, it clearly looks like a circular cylinder. That's really not the question. It's how would I find the volume of the thing that I'm actually holding? Well, the thickness obviously would be important. But what if I thought of it this way? Well, if I want to find the volume of the thing I'm holding, let me start by peeling off one layer at a time. And one layer would be a piece of paper, okay? So this is one layer. Now, when I open it up, clearly I have a big area, but it's very, very thin. So think of that like your delta X. My delta X would be very, very small, but my area might be very, very big. So for me to find the volume of this, I'm going to peel this away. Okay, and so the volume of this thing would simply be its area times the thickness. And what is its area? Well, base times height. Oh, well, that makes it really, really simple. If the volume of this, think of this as the piece of paper. It's the area that I'm looking at times the thickness. So to find the volume of a piece of paper, but isn't a piece of paper two-dimensional? Yes, but there is some thickness. I mean, it is very thin. I mean, a fraction of a millimeter, but there is actually thickness. So this piece of paper actually has volume. So when I fold it up or I roll it up, it's the volume of the circular cylinder, the container itself, not what it holds. And that's what's a little bit different. So if I were to find this sort of volume, clearly it's going to be base times height, okay, times thickness. So this thing right here, if I said generically, let me do a really simple example. So I've got something, let's say y equals f of x. This is the sort of the usual thing. And I want to take this thing here and I want to rotate it about the y-axis this time. Okay, so clearly I have a three-dimensional solid, something like that, and it clearly is, it's a torus, it's a donut, right? I have a big hole in the middle. You go, okay, great, we already know how to do this. The problem is if I try to use the disc/washer method and I do my horizontal slices, do you see a problem when I get up here? My slices will be changing all over the place as I'm hitting the different parts of the curve. I really don't want to slice horizontally. Oh, horizontal slices would be great down here. But up here, I have this slice, and then over here I have maybe this slice, and over here maybe I have this slice. It would be too crazy. I really would like my slices to be vertical. But you say, how do I do a vertical slice? My vertical slices would not be circular. No, they wouldn't, unless I slice like this. I'm going to take my circular cylinder and I'm going to slice this way. Meaning, when I do that slice, this slice here is going to look like a circular cylinder. So again, I'm going to take my piece of paper that I've wadded up. I'm going to slice it like this, very thin, and that's going to give me exactly this shape. So if I asked, what's the volume of that thing that I just sliced, you'd say, well, let me open it up. We just did this a moment ago. It's going to have thickness. Clearly, my thickness is going to be delta X. What's my height going to be? Oh, that's clearly going to be the Y. And what's this length? Now, this is not clever. This should be fairly simple. If I said, what is the length of that circle? What's another name for the length of that circle?
The diameter?
Not the diameter. That.
Circumference.
The circumference. But by the way, diameter certainly involved somehow. So if I said, what's the circumference? Isn't that the same as the length of this side? Everybody see that? The length of this side, when I roll it up, is the circumference of the circle. Oh, and is the circumference 2 pi r? So this length is 2 pi, but what's r? R would be from the center to here. That's just the x distance. So that means that if this length is the circumference of the circle, so 2 pi times the radius would be from the center to the outer edge. That would be my x, not all the way across. No. That would be diameter. So then the volume of this ith slice is 2 pi xi, yi, delta xi. So at some point I would swap out yi for f of x probably. Now, the reason I don't put the f of x now is because also we could rotate this around the x-axis. We could do all sorts of rotations here. But let's start with this. Now, if I then add all of these up, then that makes for a really nice integral. Now, this one here has a name that does not make a lot of sense to people, but the technique. So I'm going to give you a little bit of history so you know where where the name comes from. I'm using circular cylinders to do my slicing. Okay. Many years ago, I spent a little time in New Orleans. I was going there. Actually, it was the AAU National Championships of karate. I did actually really well at that tournament and had a lot of fun in New Orleans, Bourbon Street, all this. And there are so many street hustlers and there are so many crazy things going on. And one of the things I was watching, I did not gamble, or there's a guy sitting at a table and he's got the marble and he's got 3 cups and he's doing this sort of thing. Some of you may have seen that. And then, he lifts up the cup. And so he'll ask, William, can you tell me which cup the marble's under? And you're following along. And you're like, that one. And you're like, you're right. Now, do you want to do it for money? So hopefully you said no, because then he does the marble, he does it, and he lifts it up and there's no marble there. It's under a different cup. This is one of the oldest con games actually in the history of the world. Does anybody know what this game's called? You probably all seen it. Heck, if you went to a Gulls game, they do this with the helmets, and you're trying to guess which one the puck is under.
I've seen it, but I've never heard what it's actually called.
It's a shell game.
See it?
The shell game.
The shell game. It's called the shell game. So why am I telling you that? That's the name of this technique. This is called the shell method. And you'd be saying, okay, I'm not seeing the connection between cutting these things with circular cylinders and calling it the shell method. The shell method comes from the name the shell game because the things you're moving around technically are circular cylinders. Yeah, that actually the name of the technique comes directly from the con game, which I find to be really, really cool. I don't know, maybe the mathematician who came up with this had just, lost all of his money to a con man and said, oh, okay, let me name my technique after him. So this is called the shell method. And you need to know that because if you're using the shell method, you have to know this is the one it is. It's the one where I take my circular cylinder and slice it. It is completely different than the disc washer method. And I'll show you why it's absolutely different. We're going to look at a couple of problems that we looked at last day, but we're going to look at it from this point of view. Okay, so let's, the region bounded by, let's say y equals x squared. I'm going to keep this simple. Y equals x squared, y equals 9, and x equals 0 in the first quadrant. Is rotated about the y-axis. Find the volume of the resulting solid. Okay, so what am I asking you to do? I'm asking you to take this region right here and then rotate it about the y-axis. Okay, so we get this. Does anyone remember what the actual name of this is called? I'm just curious. You don't need to know this, but in Calc 3,
Paraboloid.
yeah, circular paraboloid. The circles, because the cross sections would be circular, they could be elliptical, they could be anything. It's called a circular paraboloid. It's a gumdrop, it's a bullet shape. I want to find the volume of this. So what we did last day was we did horizontal slices because horizontal slices ensured that we got discs, and that made our life really easy. But in doing horizontal slices, then I have to kind of change my orientation. I want to use shells. So what I want to do, once again, I'm going to take my shell, and I'm going to slice it, okay? I'm going to slice it vertically. And what that will do is give me pieces that look like this. Another way of thinking about this might sound kind of funny, but if I said, think of a roll of toilet paper. If I said, what is the volume of the roll of toilet paper? You'd say, I don't mean what it holds. I mean the actual paper itself. As you unwrap the paper, right, each one is really thin, but each sheet would actually have a volume. It takes a lot of sheets to make the roll of toilet paper, but in a sense, that's kind of what we're doing here. I'm from inside to outside. So think of it this way. I have a tiny shell and a bigger shell and a bigger shell and a bigger shell. I'm going to fill this thing up. See, my thinnest slice will go all the way down to the bottom. And I'm going to fill this up, right, with n slices. And then eventually, obviously, we'd take a limit there. So what is the volume of this piece right here? So I'm going to open it up just so we know what it is we're looking at. My thickness clearly is, if it helps do this. My thickness is delta x. So a little roll of toilet paper there. From here to here is x. Okay, that's my radius. And remember, we said this was the circumference, so this would be 2 pi xi. Right, we're not going all the way across. We're going from here to here is the radius. This is the circumference. Now, what is my height? My height is this. My height is not going all the way down. Oh, so my height would be the difference between this y value and this y value. So my height would be the difference between y equal 9 and y equal x squared. Okay, so if I just generically call this yi for a moment, and we said our volume is 2 pi xi yi delta xi, well, that's going to be 2 pi xi, and we said the difference here, so that would be 9 minus that. Okay, because that's what that height would be. The x's are going to range from what to what? Well, in the XY plane, that was y equal x squared and y equal 9. So that would be the 0.3 comma 9. Now here's the tricky part. What is x ranging from? Is x ranging from -3 to 3? This is not obvious, but I want this to be an absolute certainty for you. What do you think the range of values for x is?
0
9 to
to
-9?
X.
Well,
Not
it
a
is,
9 is a y value.
is it 0 to 3?
Why
yes.
0 to 3?
It's only-
Because you're talking about the radius, so it's half the circle.
Beautiful. Perfect. Stop it. I'm not worthy. That was awesome. Because x represented the radius. X is not the distance all the way across. X is the distance from here to here. Oh, x represents the radius, and the thinnest shell would be at 0. The widest would be at 3. This is the most common problem people have, is they're not thinking that it's the radius, so they're going to go all the way across and go -3 to 3. But if x represents the radius, I can't have a negative number. That don't make no sense. So it's the radius, because remember, these are going to end up being my limits of integration. The problem with going -3 to 3 is that half the problems you do, if you do that, you're going to end up with an answer of 0. And that's probably not good. So what we're going to get then is the volume is, I'll put the 2 pi on the outside, 2 pi times the integral from 0 to 3 of 9x minus x cubed, which, by the way, is an odd function. So if I had gone -3 to 3, that absolutely would have given us an answer of 0. And we know 0 is not a good answer in this case. So when I do this, 2 pi times 9/2 x squared minus 1/4 x to the 4th from 0 to 3. Don't run out of room here. So 81/2 minus 81/4. So my final answer is going to be 81/2 pi. Okay. Now, just for comparison purposes, what if we had used the disk washer method? Okay, if we had used the disk washer method, let me erase. Actually, no, I'll just draw a picture above it. Same problem. Now we're going to say, let's slice it so my disk would look like this. Okay, I can't do disks very well. Now my radius obviously is the x. My thickness in this case is the delta y. So my ith volume would be pi r squared. So pi xi squared delta y. Now I need to change everything to y's, but remember this curve is y equal x squared. So this becomes pi yi delta y. And the y's would range from 0 to 9. All right, so my volume is pi 0 to 9 y dy, which is pi over 2 y squared from 0 to 9, or 81/2 pi. Of course, it's going to be the same answer, but the integration looked very different. Okay, doesn't even look like the same problem. Well, the nice thing is, okay, go back to area for a moment. Now, I said this before, when finding the area of a region, you can set up every problem with delta x or delta y cuts, and you make your choice on which integration is easier. So like on the bonus problem on the quiz, people looked at that and said, oh, if I do delta x cuts, I'm going to have to try to integrate inverse tan of x, and we don't have an antiderivative formula. But if I do delta y cuts, then I'm going to be integrating tangent of y. Oh, I know how to do that. So the rule of thumb is you picked whichever way you thought would present an easier integral, knowing you can absolutely always do every problem either way. Usually one is more efficient than the other. Well, it turns out the same thing is true with volumes by rotation. When I take a region and I rotate around the x-axis, or I rotate it around the y-axis, every single problem can be set up either as a shell or as a disk/washer. And you would simply choose it based on which you thought was easier. Okay, there was no wrong way to do it, but more often than not, one way might be more efficient than the other. Okay, so let's do another one. eraser's starting to die on me here. All right, let's do the following. The region bounded by y equals, let's do a simple one. So we like simple better. How about 10 over 1 plus x squared, x equal 3, and let's see, y equals 0, x equals 0 in the first quadrant, is rotated about the y-axis. Let's find the volume of the resulting solid. A little tight here. All right. Well, maybe the most important part of this is to draw a picture. Okay, because without a picture, I don't actually know what I'm finding. Well, this here basically looks like this. I'm cutting it off. Let me have it drop a little bit faster. Sorry. I'm cutting it off here at x equals 3, x equals 0, y equals 0, and I'm going to rotate this about. We're going to do this. So what we're going to get is, I don't know what you call that thing. It's this thing in 3 dimensions. Okay. I don't know. I wouldn't call it a cake, but it's
through camel's hump.
I'm sorry.
It's a camel's hump.
Yeah, sure. It's a camel's hump. All right. So we want to find the volume of the camel's hump. So I have 2 ways I can do this one. Because the rotation is this way, if I do my slices horizontally, then those would represent discs, obviously. If I want to use the shell method, that means I'm slicing this way. So what I want to do in this problem is I want to do it both ways so that you could say, oh, you know what? This way might have been better than that way. There's no wrong answer. So let's start with the horizontal slices. All right. So without me even drawing the disc, the volume of a disc is just pi r squared times the thickness. So let's call that the ith volume. So my radius is clearly the x. So pi xi squared delta yi. Now I want you to notice something. That's going to be, my outer edge is going to be this curve until I get to here. Does everybody see that? Because this piece right here, that's just a simple solid circular cylinder of constant height and constant radius. Ooh, so I can actually calculate this volume and just add it to. I don't have to integrate this piece. I can just calculate it. I only have to integrate this piece. Now, this x value is 3. So what's this point right here? This would be 3 comma what? If x is 3, what's y?
1.
Yeah, that's good to know because that will affect perhaps those limits of integration. I want to have that. Okay. Now I got to integrate this with respect to y, which means I need to replace x squared with something y-ish. Ooh, that might not be that easy. So let's do a little bit of algebra. I need to write x squared equals. Well, the first thing I'm going to do is take the reciprocal of both sides. Oh, that makes it a little easier. So do a little flip-flopping here. How about 10 over y equals 1 plus x squared? So x squared would equal 10 over y minus 1. Oh, okay. Not trivial, but not that hard. If I wanted to solve for x squared, we just did. Now, I have to do that because I need this integral to be in terms of y. So this would be pi 10 over yi minus 1 delta yi, and the range of values for y, well, let's see, that point there is of course 0 comma 10. If x is 0, y is 10. So my y's are going from here to here. So the y's will be going from 1 to 10. That will now give me the volume of that thing. I'm looking at that thing and I'm seeing some chocolatey dessert-like thing, but that's just me. Yeah, don't worry about that. You know, some sort of bonbon kind of thing. I don't know. So let's find the volume of that thing. So now my volume is, okay, pi. I always pull the pi out. There's no reason to leave it in the integral. The integral from 1 to 10 of 10 over y minus 1. And that's not that terrible. Okay, what does this give us? This gives us pi times, that will be 10 natural log of the absolute value of y minus y from 1 to 10. That's pi times 10 log 10 minus 10 minus 10 log 1 minus 1. Okay, everybody got that so far? Well, log 1 is 0, so I'm negative 10 minus negative 1. That would be pi times 10 log 10 minus 9. Or how about if I write that as, how about 10 pi log 10 minus 9 pi. Okay, now we still have to add that piece. So let's call that, how about volume 2? But I don't need to use calculus to find that piece. That's a solid circular cylinder. Its volume is pi r squared times its height. Well, what's the r? 3. What's the height? 1. And that would be 9 pi. So the volume, actually, let's call this volume 1. The volume of my bonbon was this. The volume of its thick, chocolatey, hard base, clearly that would be hard chocolate, that'd be soft, is 9 pi. I'm going to add this to this and then say then the total volume, how's that? Is 10 pi log 10 minus 9 pi. Oh, plus 9 pi. Big yikes, but we're there. 10 pi log 10. That is the answer to the problem. That's using the disk method. Now I want to do the same problem using the shell method. Say, why would I want to use the shell method? Well, first of all, rewriting this in terms of x equals was actually a little bit of a challenge. And in fact, in a lot of cases, that might not really be doable. That might be harder than we realize. I really don't want to rewrite the function if I don't have to. So I'm going to give you, after we do the problem, I'm going to give you some suggestions of how you'd know which method to use. Because there actually is a really simple way to make my determination. So now what I want to do is I want to slice this using my shells. So going this way, so an arbitrary shell would look like this. Okay, my toilet paper roll. So now the nice thing is I'm starting in the center and I'm moving out all the way to the edge. My boundaries never change because the top curve will always be this guy. The bottom will always be the y-axis. And I just happen to stop there. So this means I don't have two separate problems that I had to calculate. I just got to do one. So now I can say the volume of my ith slice is 2 pi radius, which would be x, height, delta xi. Now I'm going to replace this with this. I'm just going to replace it completely. So 2 pi xi times 10 over 1 plus xi squared, delta xi. And the x values will range from what? What will x range from?
0 to 3.
0 to 3, because again, it's the radius. So I don't like the way that looks. I'm going to pull the 10 out. I'm going to move stuff around a little bit here. What if I rewrite that as 10 pi times 2xi over 1 plus xi squared delta xi. I just swapped, I moved a couple things around. All right, so now my volume is the integral, 10, I just pulled the 10 outside, sorry about that. So 10 pi times the integral from 0 to 3 of 2x over 1 plus x squared dx. Well, clearly that's going to involve a substitution. So what we're going to do, I'll do it over here because I'm going to run out of room. If I have u equaling 1 plus x squared, then what's du? Well, that's 2x dx. Oh, I already have it, don't I? That makes it kind of easy for me. As x ranges from 0 to 3, u will range from, let's see, when x is 0, u is 1. When x is 3, u is 10. This is already perfect. So this will be 10 pi, integral from 1 to 10 of 1 over u du. And that will be 10 pi natural log absolute value of u from 1 to 10. Now, I already know log of 1 is 0, so this is just going to be log 10. And I'm pretty sure that was the answer we got the first time around. But this one seemed a little bit shorter. In fact, my integration seemed actually less challenging. Now, getting the same answer is not the big deal. Well, of course, we're going to get the same answer, but it's how we did it. So there's a really simple rule of thumb to follow. It's not something as an absolute guideline, but how do I know if I should do shells versus discs? I mean, some people say, well, you always do it this way. Anybody who says always do it this way is going to be wrong exactly 50% of the time, because there is no always do it this way. Nope. Always do shells. Nope. Of all the problems that exist, I checked last night, all the problems that exist, exactly half of them should be done using shells and exactly half should be done using discs and washers. So our question is, how do I know? Well, that's actually the easiest part. So I'm going to draw you a simple picture. This is a guideline to help you so you don't have to trial and error. The one thing I don't like seeing people do is start a problem and then say, nope, that's not going to work. Let me try it a different way. I'd rather you try it the right way the first time you try the problem. So let's make it really simple. Let's say I'm bound by, I'm going to keep it really simple. This is y equals f of x, and this is y equals g of x. Okay, I've got this region right here. Now there's two different ways I can rotate this. I can rotate this about the x-axis. I'll do my best here. Okay, so what is the shape that I would get if I do this? You know, it's basically this particular donut. Now, again, it doesn't, disc and washer is the same method. Now, I'm going to make you a little chart here. All right. Actually, you know what? I'm sorry. I'm going to make this even easier. Sorry, I'm not going to have a second function. Sorry about that. I want to make this. Yeah, that was almost too much stuff going on there. I'm just going to do one function. I'll have it go down to the axis. That just makes it a little easier. All right. So there. So now, close enough. So now we want this way. So I've got this thing, whatever it is, candle holder, I don't know. All right, so now here's what we have. We have the boundaries. Oh, shoot, I'm not gonna have enough room, sorry. I'll put way over here. Boundaries. I'm used to having a bigger board. All right, y equals f of x, or x equals, let's say, g of y. In other words, my boundaries are, in this case, I'm bounding it by a function of x as opposed to a function of y. And then my rotation is x-axis or the y-axis. So there's four possibilities here. I'll make it really simple. There's four possibilities. I'm bounded by y equal f of x and I did an x-axis rotation. Boom. I'm bounded by y equal f of x and I do a y-axis rotation. Oh, so same, we'll use the same region, but now we're going to do a y-axis rotation. Now, simple rule of thumb, when your boundaries are given as y as a function of x, you really want to maintain delta x cuts, because to do delta y cuts means you have to rewrite all your x's in terms of y's, which can be very complicated. And in some cases, it might not even be possible. But it's always more challenging when you have to rewrite your boundaries. So I really want to maintain delta x cuts because my function is given y as a function of x. So in this case, delta x cuts would clearly be disks. So if this is the case, I'm going to use the disk/washer method. But when I take the same region and I rotate it this way, if I tried to do horizontal cuts, you realize when I get at the top, I'm going to have to be doing multiple integrations. I'm actually going to have to do several integrals because my boundaries will keep changing as I move up. So I want to maintain the delta x cuts. But when I did this y-axis rotation, the shell method is the only way to maintain delta x cuts. This is not absolute, but I'd say it's 99.987% of the time you're going to follow this model. Because if I try to do disks and washers on this one, it's going to be horrific almost absolutely 100% of the time. No, you want to use shells in this case. Now, x is given as a function of y. That would also mean that I probably want to use that kind of cut. So let's look at that one. I'll keep it really simple. So I've got, let's say, there. I got that thing right there. I'm bound by, this is now x equals some function of y. Let's start with a y-axis rotation. So what I've got here is, again, my cool candle holder or whatever you want to call that thing. It's a blob. Now, if I do vertical cuts here, then my boundaries may be changing as I get near the edges. No, I absolutely want to do. That's a no-brainer. I definitely want to do horizontal cuts there because now it's disks. My boundaries never change. I don't have to rewrite my function. So x is a function of y, and I did a y-axis rotation. I want to do disks, washers. I'll actually have people tell me, no, you always do disk washers for everything. Or all x-axis rotations should be done using this technique. Really? So all y-axis rotations should be done? Oh. Anybody want to guess what's going to go here? Just guess.
Shell.
It's going to be shell. It's not even close. And I'll show you why. Now I want to go this way. If I do vertical cuts, again, I have to rewrite my boundaries, and that might mean 3, 4, 5 integrals. Yeah, I don't want to do that. Nope. I want to maintain horizontal slices so that I don't have to rewrite. But to maintain horizontal slices now means I've got shells. This is what I would follow 100% of the time. Now, I don't have this written off to the side. No, not even close. What I'm saying is, if your boundaries are given as functions of x, you want to simply maintain delta x cuts. You want to maintain vertical slices. But an x-axis rotation would mean disks and washers. A y-axis rotation would mean shells. That's the only way you can maintain the delta x's. And then the same thing here, it switches. Okay, so it's a simple rule of thumb that you want to make your integration as easy as possible if you can actually call an integration easy. So when you're doing a problem, if this were the final exam, I'm going to say it's rotated, find the volume. I'm not going to say which method to use. You're going to look at it and go, I think this will be easier using this technique. But if what you do is correct, it's correct. Okay, you just want it to be the most efficient way, so you do the least amount of work. So that's the shell method. It goes hand in hand with the disk washer method. Now, we're going to do a different type of volume, one that does not involve rotation at all, but involves some level of consistency. So here's what I want you to imagine. I've got a big lump of cookie dough, huge. Okay, it could be bad cookie dough, so you're not going to get hungry. I have a big, massive thing of cookie dough, and I'm going to set it flat on my table, so that it's perfectly flat on the bottom. That's very important. It's bound by, my table is going to be the XY plane, by the way. So it's bound by that. but there's a consistency of my cookies. When I slice them in a particular direction, either perpendicular to the x-axis or perpendicular to the y-axis, when I slice them, I will always see the same shape. Now, that shape can be anything, but in this context, that shape's usually going to be triangles, rectangles, circles, something, a very simple geometric shape. Because if we make the geometric shape too complicated, we won't be able to do the problem. So that's the idea. So let's we have, let's do it this way. Find the volume of this solid with base, keep it real simple, x squared plus y squared equals 16. And slices perpendicular to, let's say, the x-axis are squares. Now, this is a good starting one. Let me just make sure of something here. Hold on a second. I want to make sure I didn't ask you this question already. Okay, good. All right. I have a really bad habit of when I just make up problems off the top of my head, they end up being problems that I had already put on a quiz. And so I end up doing the quiz problems for people. I know you would love that, but I'd rather not do that. All right. So what the heck is this looking like? Well, in the XY plane, I'm bound by a circle. When I make my slices perpendicular to the x-axis, this slice here looks like a square, which means, no, this is terrible. I know this is coming out at you. This is looking like a square. So these slices are short. They're getting longer as I'm coming out, and then they're going back in. So what I'm seeing is almost like kind of like a runway. By the time I'm here, I'm really far away. You can't see that because of dimension. So again, the slices here, this would be a small square, right? It's coming out as a square, it's getting bigger and bigger and bigger and coming back in. That doesn't have a name, this shape. I'm just telling you what the cross sections look like. Now, what's going to make this work is the fact that it's flat on the bottom. I'm bound by a circle on the bottom, and all of my slices are what we'd say is similar. They're not congruent. Congruent would be identical, but they're all squares. Now, they're squares of varying sizes because the square here would be huge. The square here would be short, but it's still a square, and that's critical. So what is the volume of this piece right here? Well, let me just take it down. Let me just take it out. It's a square. Now, the thickness of my square, clearly delta x. But what's the height of my square? Ooh. Well, we agree from here to here, that would be y. So what is it from here to here?
Y times 2.
Exactly. If this is y, this is 2y, it's a square. So that's 2y, that's 2y. By the way, this step right here that I'm doing is the most important part of the entire problem. If I don't figure out what the volume of an arbitrary slice is, there is no integral. But this should never be difficult. How do I know it looks like this? Because I said the slice is a square. But I'm slicing it perpendicular to the x-axis. This means ultimately I'm going to be doing x-ish stuff. So this times this, that would be 4y squared delta xi. Now, you've noticed this is a common theme. When we did the discs and washers, and we did the shells, that when I'm writing my volume, more often than not, these variables are not the same. That's okay. I'm writing an arbitrary slice. But when I go to integrate, I cannot have y dx. That won't work. So now I need to replace the y squared. Well, how am I going to replace y squared? What am I going to replace y squared with? I need a relationship between x and y. Well, I'm bound by that particular equation. So do I have a relationship between X and Y? Yeah. Okay, so what's the value of Y squared? That would be 16 minus X squared. That is critical that I recognize that. Okay. If the base had been something more complicated, I could still do this problem, but this would have been difficult, this step right here. If this wasn't a square and something more complicated, this would have been more difficult. I could still do it. So we tend to do it with friendlier shapes so we understand and we can navigate through. Now, what is the range of values for X? This is a circle of radius 4. So I know that point right there would be 4, 0. I know that point would be negative 4, 0. So the range of values for X would clearly be then. See, X, there's no, don't worry about radius. Just X's are going from negative 4 to 4. Okay, so my volume is, go ahead and distribute that. The integral from negative 4 to 4 of 64 minus 4x squared. Okay. Now, do you notice anything about my integrand and my limits? Anybody?
It's symmetric and even.
Perfect. Symmetric limits, even function, definitely want to double. There is no exception. This will always make the problem shorter. But you've added a step and I've eliminated 3 others. Yeah, I always take this route every time. So 64 minus 4x squared dx. So that will be 2 times 64x minus 4/3 x cubed from 0 to 4. Okay. It's going to be a little bit hard pressed. So 64 times 4, that'd be 256. 4/3 times 4 cubed, that'd be 256 thirds. So when I do that, that would leave me what, 1,024 thirds pi. Okay. Now that's it. I'm sorry. Sorry, there's no pi. Sorry, 1,024 thirds. I think that's correct. Of course, use your graphing calculators if you have to do the fraction. No, I'm joking with you. Now, my base is a circle, my slices are squares, and my answer is 1,024 thirds. Is there something conspicuously missing from this answer? My base is a circle.
There should be pi in it.
It feels like there should be a pi in it, but pi never showed up in the calculation because my volume was not dependent on the circle. My volume was dependent on the fact that these are little, basically, technically called rectangular prisms. They're little flat wafers. I have a whole bunch of little flat wafers of varying sizes and I'm adding all of their volumes up. There's no pi in there. Well, but there's a circle. Yeah, the circle only is the relationship between the X and the Y, isn't it? Oh, now I'll tell you where pi would come up is if my cross sections were circular, then I would have a pi come up. That's the only way that the pi can come up. Okay, so let's do that one. Similar problem now. Find the volume of the solid with the base. I will do a similar problem to this one, but it will not be the same problem. Actually, I need to erase everything. Okay. All right, find the volume of the solid with base. Let's say this time x squared plus y squared equals r squared, r being the radius of the circle, r is a constant. Okay. Let's say slices perpendicular to the y-axis are semicircles. Oh, and find the volume. That's sort of the ODA. Yeah, find the volume. Now let's see. So what does this one look like? Slices perpendicular to the y-axis this time. So these, semicircles. Small semicircles, big semicircles. Anybody see it?
It's a sphere.
You're half right.
Sorry, half a sphere, the hemisphere, or whatever.
It's a hemisphere. Now, you can say, oh, it's a snow globe. It's one of those Bosu or whatever you call them, balls they have at the gym, you know, the squishy things that people do their sit-ups on and stuff like that. It's a half of a sphere. Why is it a half of a sphere? Because I'm only doing the top half, right? Because I'm bound by this. But basically, that's a fairly complicated shape. But my cross sections are semicircles. So small semicircles, you know, big semicircles, small semicircles. But Nate's absolutely correct. This turns out to be a half a sphere. Now, I find this interesting. I have fun with some of the language parts. I'm bound, or my slices are semicircles, but you said it is a hemisphere. What's the difference between hemi and semi?
HMS.
Yeah, good. That's the best. It's a Latin thing. And I have fun with that because a lot of people say, wait, in Latin, there are words that begin with H and words begin with S that are exactly the same words. In Japanese, G and K. It's very common. To kick in Japanese is geri, G-E-R-I, or it's keri, K-E-R-I. There are many words. It's basically the same word. Well, in Latin, there's a lot of words. Seven. There's two different prefixes for seven. In the Olympics, the women do a 7-event thing. The men do a 10-event thing called the decathlon. The women do a 7-event thing called, anybody know what that's called?
Heptathlon.
Heptathlon. Yet hept is 7. But if you're in your 70s, you're a septuagenarian. The original 7th month in the Roman calendar was not July. Remember, July and August, I had fun with this one. July and August were added. They were named after a couple of Caesars. You'll never guess which ones, you know, July and August. Julius and Augustus. The original 7th month, September. The original 8th month, October. Oct is 8. 9th, November. Nov is 9. 10th, December. DEC is 10. A lot of people don't realize that the months were named after what month of the year it was. It was July and August being added. But a septuagenarian, someone in their 70s. A 7-sided figure is called a septagon, although it is acceptable to call it a heptagon. Talk about confusing. Yeah, in Latin, S and H are often interchangeable and it's the same word, but you want to know the context. Semi and hemi mean exactly the same thing. So if I said semi versus, you know, we sometimes say semi and hemi. It doesn't matter. It's, you know, what is it? A potato, or something like that. Do you know the context? This is important. When you use semi in a math, geometry, engineering environment, typically you use semi if it's 2-dimensional. Hemi, 3-dimensional. That's it. So we say a hemisphere because it's half of a sphere. We say semicircle because it's half of a circle. That's not a right or wrong. That's just been the convention for, you know, hundreds and hundreds of years. But I find it interesting because it's a language thing. I wasn't there when they decided that, you know. So the 7 is a weird one, but that now you can go back and see context. Oh, okay, I see words that seem like they're the same word, but you know, different. By the way, that's 7. What about 6? There's 2 different words that mean 6 in Latin. You know what they are? What's a 6-sided figure called?
Hexagon.
Hexagon. But if you have 6 babies at one time,
The
they're not called hextuplets. They're called, you know what they're called?
sextuplets.
Sextuplets. Sex and hex both mean 6. And again, the same as hept and sept, both mean 7, but it's a context thing. Some words you say sex, some words you say hex. That's crazy. So my all-time favorite, somebody in their 60s. The actual formal English word for somebody in their 60s is a sexagenarian. That's not a joke. I think that's one of the coolest words in the English language. A sexagenarian means you're in your 60s. Not a hexagenarian, sexagenarian. So anyway, getting back to it's a hemisphere. So if I take an arbitrary slice, this is what I'm going to see. Give it a little perspective here. Yeah, okay, you guys can see it, right? That's kind of, all right, I need to find the volume of this thing. This is a little trickier than a square. All I need is the radius. By the way, I don't need the height, it's a semicircle. Oh, okay, what is the area of a circle? Anybody? Area of a circle?
Pi r squared.
Pi r squared.
Pi r squared, so what would the area of a semicircle be?
Pi r squared divided by 2.
Yeah, so this is going to be, sorry, my ith volume here is going to be 1/2 pi r squared. Now, what is my r? In this case, my radius is clearly the x. Okay, that's x. My thickness is clearly delta y. So when you stare at that, the volume of that slice, now my answer is going to have a pi in it, definitely. Okay. I need y, so I'm going to replace x squared with something y-ish. So I'm going to replace x squared with r squared minus y squared. And if you want to put pi over 2, that's fine. And so this would become r squared minus xi squared. Yi squared delta yi. Y ranges from, what's y going to range from? Well, y is actually going from here to see. The radius is x, but y is going from here to here. So what is the range of values for y?
It's r to negative r.
Yeah. So therefore, my volume is pi over 2 times the integral from negative r to r of that. R squared minus y squared dy. And once again, r is a number. R is not a variable. R is a constant. A constant has degree 0. So this is an even function, symmetric limits. So once again, I can double it. Okay, that just makes it pi 0 to r squared minus y squared dy. So that will be pi times r squared y minus 1/3 y cubed. Again, r is a constant. So that's 0 to r. So when I replace y with r, this is going to be r cubed minus 1/3 r cubed, which would be 2/3 r cubed. So this would be 2/3 pi r cubed. By the way, what's the volume of a sphere?
2/3 pi r cubed.
Half right. The volume of an entire sphere is 4/3 pi r cubed, isn't it? Oh, so could we use this to derive the volume of a sphere? Yeah, we just derived the volume of a half of the sphere. So an entire sphere would be double that. Now, here's what's very interesting about this, and I always have fun with this. In calculus, we can do things like we can find the volume of a circular cylinder. We can find the volume of a sphere. We just did. We found the volume of a half a sphere, so the volume of a whole sphere would be double this. We can find all sorts of volumes of geometric shapes using the calculus. Okay, but again, we're using calculus to find the volumes, but the ancient Greeks knew this. They knew these things. So that's one of those questions. If the ancient Greeks knew these in the 4th century BC, they knew pi. They knew the area of a circle and the volume of a sphere and all this. Calculus was invented in the 17th century AD, about 2,000 years later. It is not possible to come up with the 4/3 pi r cubed without using calculus. It's actually not possible. There is no cleverness. There's no way you can come up with pi r squared without using calculus. So if the Greeks, ancient Greeks knew it, but we couldn't actually come up with it as a conclusion for 2,000 years. We couldn't prove it. We had no way of knowing that it was true. How did the ancient Greeks know it? That's one of those awesome questions that I would love to know before I die. Anybody want to speculate? How did the ancient Greeks know all of these formulas that require calculus to prove, but couldn't be proved for 2,000 years? I have a theory myself. I've watched Men in Black enough times. I kind of know how it happened. I'll give you a hint. Same place.
The aliens.
Yeah, same place Velcro came from, and the pyramids, right? Aliens. I have fun with that, but you know, that would almost say, yeah, that would actually make some sense. So this is kind of cool in that we can do this. Now, here's our limitations on this type of problem. There's only a couple of types of bases we can have to do this in a Calc 1 class. Our bases either need to be circular or our bases need to be parabolas, simple parabolas whose vertex is at the origin. And the reason is because of the squared relationship between x and y in those two functions. Because most area functions in geometry involve the square of a unit, or think about, in other words, what are the units of area? It's whatever your dimension is squared, right? Centimeters squared, inches squared, whatever. So if I'm finding the area of a square, I know that's just side squared. The area of a rectangle is base times height, which would be the square of whatever some length numbers are. Circles, pi r squared, and so on. So if area units are always involving something squared, then what we need are bases whose relationships between the variables involve a square, not a cube, not a square root. And so we tend to make this one, I don't want to say it's dumbed down, but we tend to only stick with problems that we can navigate through. I could easily make this base not circular and complicated. I could make the cross sections more complicated. And we could still use techniques of Calc 1, but we might get integrations we can't perform. Now, in Calc 3, you're going to come back to these questions and you're going to remove all the restrictions. You see, our restrictions now require that we can write the problem with one independent variable, because that's our restriction in Calc 1 and 2. In Calc 3, we remove that restriction because we can do the calculus of multiple independent variables. So I reiterate this. In the first 2 semesters, you are mastering the calculus of real numbers in 2 dimensions. And once you master that, then you can now extend your world to 3D, because that's the world we live in. So when you're in Calc 3, I basically tell you in Calc 1 and 2, it's sort of like you did calculus with one eye closed. You see, when you close one eye, everything becomes 2-dimensional. When you open your eyes, it now becomes 3D. It doesn't change everything. What you do is you expand everything. You use all the rules you created in calcs, in 2-dimensional calculus, and extend them to 3D. Then later, if you're an engineer or a math person, you may be taking a course called complex analysis, junior, senior year over at San Diego State, let's say. That's the calculus of complex numbers. We're only dealing with real valued calculus, real numbers. Right? No complex input or output other than the hyperbolics. We never even talk about complex numbers in calculus, not until you get to that upper division course. And some of you may not ever actually take that. So mastering 2-dimensional calculus is our goal the first 2 semesters, extending it. So Calc 3 students will tell you that, they like Calc 3 better because now they can start doing real world problems. They can explain stuff that's going on in the real world. But we're doing a 3-dimensional problem right here. The difference is we're doing it with one independent variable. Later, you'll be able to do it with multiple. Okay, so that's where I wanted to get today.